So far, astronomers have found over 400. Some are colossal balls of churning gas, 5 times the size of Jupiter. Others are huge rocky worlds, many times larger than Earth. Some follow wild, erratic orbits, so close to a star, they're burning up. One thing is clear, no 2 planets are the same. Each is one of a kind. But most of these new planets are far away and hard to study. Most of what we know about how planets work comes from the 8 that orbit our own star. Our own planets come in 2 main types. There are 4 rocky planets in the inner solar system: Mercury, Venus, Earth, and Mars. And in the outer solar system, there are 4 giant gas planets: Jupiter, Saturn, Uranus, and Neptune. Each of the 8 planets is distinct and very different. Their unique personalities began to form at the birth of our solar system 4.6 billion years ago. When the sun ignited, it left behind a huge cloud of gas and dust. All 8 planets, the inner rocky and the outer gas planets, came from this cloud of cosmic debris.
The planets in our solar system are all made from the same stuff. They're made from the same cloud of gas and dust, but they formed under very different conditions. Some of them formed in close to the sun, where it was much hotter, some much farther away, where it was much colder, and because the conditions were so different, the end result, the product of that formation, was different as well.
So you start the solar system, in my view, with a pretty homogeneous mix of silicates and water vapor and hydrogen, lots of hydrogen, and methane and other elements.
These elements in the dust cloud are like ingredients in a cake. They cook differently depending on the combination of the ingredients and the temperature of the oven.
Then just like with the cake, you'd mix the ingredients and then you'd put it in the oven and bake it, and it would change. And so this is kind of what happened in the solar system. Overall, the planet cooks in a slightly different way depending on how close it is to the sun.
Close in, where it's hot, the sun burns off gases and boils away water. Only materials that stay solid at high temperatures, like metals and rock, can survive. Which is why only rocky planets form close to the sun. Move farther away from the heat of the sun, and you get different kinds of planets cooking. But it's the ingredients in the cloud that determine precisely what kinds of planets will form.
Well, depending on the type of cloud a solar system forms in, you could have solar systems that don't have rocky planets because it was just too poor in the materials to build something like the Earth, and instead you could end up with more gas giants and no rocky planets at all.
If you want rocky planets, you need a cloud full of metals and rock. Next step, turn the heat down.
As it cools down, some of the elements in there that have a high boiling point start to condense out as solids. And you can get these very tiny little mineral grains forming.
These tiny mineral grains are the seeds of a new rocky planet. Over time, they start to stick together.
You'd have one dust molecule and another dust molecule, and they would basically slam into each other and become one slightly bigger dust molecule. And they would pick up more and more and more. This process is called accretion. As these things got bigger, they became basically rocks.
Then, rocks slam into other rocks and form boulders. Boulders smash together to form bigger boulders.
Eventually, you got something big enough that its gravity was strong enough that it could start drawing material in. So instead of just slamming into material and gaining mass that way, it was actually actively pulling material in.
In our own solar system, there were many growing infant planets at first, maybe 100. Most of them didn't make it.
If you go to the asteroid belt and look at the asteroid 4 Vesta, that is a good indicator of how big a rocky planet has to be before it can pull itself into a spherical shape.
Vesta is only 329 miles across. Not quite big enough to become a sphere. For a growing planet to become round, it has to reach 500 miles across. Then it has enough gravity to crush it into a sphere. Any smaller, and it stays in irregular shape. As round infant planets keep eating up stuff, each collision makes them hotter and hotter until they start to melt. Now, gravity begins to separate the heavy stuff from the light.
Lighter materials tend to float up into a crusty film, and the heavier materials, many of the metals, falling down and forming a much denser core at the center of the planet.
The young planets are finally beginning to look like planets. But now, they have to survive a period of violence and destruction. A brutal phase that determines which planets will live and which planets will die. After the birth of the Sun, our 8 planets all evolved from the same cloud of dust and gas. And yet, they ended up completely different. There was no real blueprint for each of the newborn planets. They did obey the laws of physics and chemistry, but the most important things happened by pure chance. 4.5 billion years ago, around 100 baby planets circled our sun. It turned into a demolition derby. Planet hit planet. Most were destroyed.
The early history of these planets would have been very, very violent, with lots of these impacts taking place in the final stages of the growth of each planet. As these impacts took place, as objects ran into each other, certain objects began to grow at the expense of all the others in this swarm of planetesimals. And these planets, these things that would become planets, grew and grew, and as they got bigger, they swept up all the smaller planetesimals around them. The consequence on the surface of that protoplanet being an enormous amount of bombardment by debris from space.
When it was over, all that was left were 4 very different rocky planets.
Each planet's impact history left its stamp, and that's why they're all so different from each other.
Mars is a frozen wasteland. Earth flows with liquid water. Venus is a volcanic hellhole. And Mercury is tiny, bleak, and super hot, the result of a monster collision.
Mercury, for example, is extremely dense and has a very thin crust, so it's possible it started off as a bigger planet. And then something hit it at an angle, and it sheared off the lighter weight crust, leaving only the dense core.
The young Earth also took a big hit.
Sometime late in its development, the Earth was impacted by another object that ripped debris out of the Earth's mantle. Which then went into orbit around the Earth and reaccumulated to form what is now the Moon.
There's also evidence that something crashed into Mars. The northern hemisphere has a thinner crust than the southern.
A theory that has emerged for how this happened is that early in the planet's history, the northern hemisphere of Mars was whacked by some object that blasted a lot of the crust off of it. And that crust reaccumulated on the southern half of Mars.
All these collisions did 2 things. They cut down the number of surviving infant planets, and they brought more ingredients to the survivors.
If you had a collision with something that was metal-rich, those chunks would tend to descend down into what was becoming the core. Where if you collided with something light or icy, they would tend to just float about and form part of the crust instead.
The 4 rocky planets close to the Sun were almost complete. They had a solid, hot iron core, surrounded by a layer of liquid iron, all wrapped in a jacket of molten rock. Above that, an outer surface crust. These rocky planets all formed in the same basic way, from the same basic stuff. But each of them was very different. Different sizes and very different destinies. Space may look empty, but it's not. It's full of stuff blown out of the sun. The sun generates powerful magnetic fields that rise above the surface in giant loops. When they clash, it triggers a storm of super hot, highly charged particles blasting out into space. It's called the solar wind. Astronauts in space can see it, but only when they close their eyes.
Occasionally you see a little flash with your eyes shut, and that is an energetic particle coming through your head and interacting with the fluid inside your eye, and it makes a little light flash. And you see these every couple of minutes or so that you're awake with your eyes shut.
If the astronauts were exposed to a lot more of the solar wind, it could be a killer.
During the Apollo program, in between 2 of the moon missions, there was an outburst on the sun that would have killed the astronauts if they had been there. So space radiation is a serious business.
But here on Earth, the solar wind isn't much of a threat because we have an invisible protective shield, a magnetic field generated by the planet's core.
The very center of the Earth is the solid inner core. It's a hard iron crystalline ball. Then there's a thick layer of liquid iron, which is convecting, churning motions, which give rise to the magnetic field.
Well, that's the theory. To prove that an iron core can generate a magnetic shield, scientists built their own planet in a lab. This 10-foot, 26-ton sphere simulates conditions deep inside the Earth. A metal ball in the center acts as the planet's inner core. Liquid sodium spins around it at 90 miles an hour, imitating the effects of molten metal spinning around the Earth's core.
We built this experiment to try to generate a magnetic field to attempt to understand why the Earth has a magnetic field and why other planets do not have magnetic fields.
It works like the generator in your car, where rotating coils of wire produce electricity. In the experiment, liquid sodium churns around the core and generates a magnetic field.
It's very much like an electrical generator. You have motion that is able to generate magnetic fields by turning the energy of the motion into magnetic energy.
The same thing happens deep inside the Earth. As the Earth spins, the hot liquid metal flows around the solid core, transforming its energy into a magnetic field that emerges from the poles.
It protects the planet's atmosphere from the solar wind. And if the planet has a magnetic field, that solar wind will be diverted around the planet by the magnetic field.
The magnetic field deflects the solar wind around the planet, protecting the atmosphere and everything on Earth's surface. Sometimes big storms of solar radiation will mix it up with the magnetic field. Then we get big light shows over the poles, the auroras. Without a magnetic force field, the solar wind would blast away Earth's atmosphere and water, leaving a dead, arid planet. A lot like Mars. Mars formed just like Earth, but today it's cold and dry with little atmosphere. So why are the two planets now so different? In 2004, NASA sent 2 robot explorers to Mars to find out. The rovers, named Spirit and Opportunity, explored miles of the Martian surface. They confirmed that Mars is a dry and hostile desert with only 1% the atmosphere of Earth. But they did find evidence of water in the past. Mars was not always a desert.
We have found compelling evidence that water was once beneath the surface, came to the surface, and evaporated away. We also see in a few places ripples preserved of the sort that are formed when water flows over sand. So not only did water exist below the surface, it flowed across the surface.
If Mars had water once, it probably also had a thick atmosphere. So what happened? We can see that Mars once had active volcanoes, so it had a hot interior at some point. And because it was made of the same stuff as Earth, it would have had a hot iron core, surrounded by liquid metal at its center. So it should have had a magnetic field too. The question is, where did it go?
Early in the planet's history, Mars apparently had a strong magnetic field, and it was probably caused in the same way as it is on Earth. But Mars is a smaller planet than Earth. It's going to lose its heat more rapidly as a consequence. And what that means is that liquid core can freeze solid. Freeze the core solid, the convection will stop. If the convection stops, the magnetic field goes away.
As the magnetic shield died, the solar wind blasted away the atmosphere and the water evaporated. Mars became a cold, barren planet. Mars, Earth, Venus, and Mercury, the rocky planets, all formed within 150 million miles of the Sun. But 4 times farther out, the Sun baked a very different kind of planet. They're gigantic, they're made of gas, and these monsters have no solid surfaces at all. So far, astronomers have discovered over 400 new planets orbiting in far-off solar systems. Nearly all of them are gigantic and made of gas. We have 4 of these so-called gas giants in our own solar system.
Jupiter, Saturn, Uranus, Neptune, which all have these very thick, very soupy atmospheres, lots of hydrogen, lots of helium, lots of methane.
Why are these outer 4 made of gas when the inner ones are rocky? It all has to do with location. Out here, 500 million miles from the Sun, it's very cold. At the start of the solar system, there was some dust, but mostly gas and water, frozen in ice grains.
Where the giant planets started to form, it was cold enough to get solid snow. And we think we were able to make ice snowflakes, and these things were able to clump together to form the cores of the giant planets. We think that's maybe why the giant planets got to be so big.
There was so much ice and gas, their cores grew huge, around 10 times larger than the Earth. These giant cores generated a lot of gravity. They had so much pulling power, they sucked in all the surrounding gas and built up thick, soupy atmospheres, tens of thousands of miles deep. The larger they got, the more gravity they generated. More and more dust and debris got pulled in towards the planets, and this became the building blocks of their moons. Jupiter and Saturn have over 60 moons each. The gas planets have another special feature: rings.
Saturn is unique among the planets in that it has this gorgeous ring system. It turns out Jupiter and Uranus and Neptune, they have ring systems as well, but they're really weak and pathetic and extremely hard to detect.
But they are there. All 4 of the gas giants have rings, but Saturn's are the most obvious. From a distance, Saturn's rings look like a single, flat disk. However, they're actually thousands of separate ringlets, each only a few miles wide. When the Cassini probe flew past, it detected billions of pieces of ice and cosmic rubble orbiting inside the rings at speeds of up to 50,000 miles an hour. These bits of ice and rock constantly crash into each other. Some grow into tiny moons, others smash apart. But they never form into larger moons because Saturn's immense gravity tears them apart. Scientists are only just beginning to figure out how the rings formed in the first place. The theory goes like this. A comet smashed into a moon and knocked it out of its orbit and closer to the planet. Saturn's gravity tore it to pieces. And all of that debris got trapped in rings around the planet. But the real mysteries of the gas giants lie deep inside them, tens of thousands of miles beneath the clouds. This is where the real action is. It's a place so extreme, it challenges the laws of nature. Most of the new planets we're finding around distant stars are gas giants. They're so huge, they make Jupiter look small. But what goes on inside all gas giant planets, both in our solar system and way out there, is a mystery. We know Jupiter's dense atmosphere is 40,000 miles deep, and we can see high-speed bands of gas creating violent storms that rage across its surface. But what we don't know is what's going on deep inside, far beneath the storms. To find out, NASA launched the spacecraft Galileo on a 14-year mission to Jupiter.
2, 1. We have ignition and liftoff of Atlantis and the Galileo spacecraft bound for Jupiter.
December 7th, 1995. Galileo dropped a probe that dove into Jupiter's atmosphere at 160,000 miles an hour. Parachutes slowed it down as it dropped through the thick atmosphere. It detected lightning in the clouds and winds of 450 miles an hour. The probe transmitted data back to Earth for 58 minutes.
So people have asked me what happened to the Galileo probe that we dropped in. It didn't hit anything. It just fell continually into the Jupiter environment, and the pressure increased and increased and increased.
As it descended, it recorded pressures 23 times greater than on Earth and temperatures of over 300 degrees.
When you're in the gas giant environment and you go deeper and deeper into this hydrogen soup that has no solid surface, it nevertheless can have a tremendous weight. And so eventually you would be crushed by the overlying weight of the material that's there.
Even though the probe descended for only 124 miles before it was crushed, it gave scientists a glimpse of Jupiter's interior. But the dark heart of the planet still remains a mystery. Like some rocky planets, the gas giants have a magnetic field too. But these are off the charts. Jupiter's magnetic field is 20,000 times more powerful than Earth's. And so huge, it extends all the way to Saturn, more than 400 million miles away. Like on Earth, the magnetic field deflects the solar wind and protects Jupiter's atmosphere. When scientists studied Jupiter's magnetic field, they discovered it was affecting Jupiter's moons. The volcanic moon, Io, orbits only 217,000 miles from the planet. Io's volcanoes blast a ton of gas and dust into space every second. And Jupiter's magnetic field supercharges it, creating powerful belts of radiation.
And that makes the vicinity of Jupiter very active in many different ways. If you point a radio antenna at Jupiter, one can hear all sorts of interactions happening between the planets and the magnetic field.
This is the sound of Jupiter's magnetic field. Jupiter and Saturn don't need the solar wind to make auroras. They have huge magnetic fields that create their own. The Chandra Space Telescope took these images of Jupiter's auroras. And NASA's Cassini probe took these beautiful pictures of auroras on Saturn. These auroras are proof that gas planets have magnetic fields too. But how do gas planets generate magnetic fields? On Earth, a superhot liquid metal spinning around the planet's solid iron core does the job. Gas planets probably do roughly the same thing. But gas planets don't have hot iron cores. They formed around frozen cores of dust and ice. So exactly what's going on deep inside is a mystery.
At the very deepest interior of Jupiter, we really don't understand what composes those deep interior states. So it could be that the very center of Jupiter has a solid core, or it could actually just be still fluid.
We may never find out. No probe could ever make the 44,000-mile journey to the planet's center to investigate. Galileo was crushed before it got anywhere near the planet's core. So now, scientists are recreating Jupiter's interior, right here in a lab on Earth. Here at the National Ignition Facility in Livermore, California, they're simulating Jupiter's core using the world's most powerful laser.
This facility is really designed to compress hydrogen to extreme densities and temperatures.
Inside Jupiter, extreme pressures are created by the weight of 40,000 miles of hydrogen gas crushing down on the core. In the lab, it's done by focusing 192 laser beams on a tiny sample of hydrogen. As the pressure in the sample reaches over 1 million times the surface pressure on Earth, the hydrogen turns into a liquid. But when it reaches tens of millions of times the pressure, more like at Jupiter's core, something really weird happens to the hydrogen.
The pressure is so great that it actually rearranges the hydrogen, which is a very basic molecule, until it is able to conduct. So it changes the structure of H2 into a metallic form.
Scientists think this is what's happening inside Jupiter. Pressure and heat have transformed the planet's core into metallic hydrogen. Jupiter's metallic core works like the iron core in the Earth. It generates the gas planet's gigantic magnetic field. Gravity and heat shape how planets evolve, from their inner cores to their outer atmospheres. They're the great creative forces in planet building. But there's another ingredient that has a lot to do with how planets turn out. And that ingredient is water. Planets may seem fixed and unchanging, but they never stop evolving. In our own solar system, one lost its atmosphere and became a barren wasteland. Another heated up and became the planet from hell. Planet Earth has changed as well, and the game changer was water. When you look at Earth from space, you see a lot of water. We are the blue planet after all, so it must be really wet, right?
It looks at first glance that our Earth, of course, covered 3/4 by oceans. It's a very water-rich world. Not true. The Earth by mass is only 0.06% water. There's some water on the surface in the form of oceans, some water trapped in the mantle, but actually the Earth is a relatively dry rock.
All of the inner rocky planets formed very close to the sun, so they started off dry. Any water they might have had evaporated away or was blown away by impacts.
These massive collisions that formed the Earth were so energetic that any water that had been here would have been vaporized and lost from the Earth.
So where did Earth get all the new water we have today? It moved here.
When you look farther out, and you look at Jupiter, Saturn, Uranus, and Neptune, those planets have enormous amounts of water locked up inside them. And even more dramatically are the moons. The moons of Jupiter, Saturn, Uranus, and Neptune are at least 50% water.
There was a lot of water out there, so how did some of it get to planet Earth?
And the answer almost certainly is that left farther out in our solar system were some asteroids and some comets, far enough from the sun that they could retain their water.
Millions of these watery comets and asteroids came flying into the inner solar system. And some of them smashed into Earth.
Over the eons, the Earth acquired the water that had been a part of the asteroids. And that indeed makes up the mass of water that nearly covers the Earth today.
But the amount of water that was delivered, that was the luck of the draw.
Couldn't it have been the case that the Earth would have acquired maybe half as much water as it did? If so, the Earth would be nearly dry on its surface, if not completely dry, the sponge of the interior soaking up the rest of the water.
No surface water would have meant no life. And what about too much water?
We would be a water world. The oceans much deeper, covering the continents, even Mount Everest. And so you can ask then, if the Earth were covered by water, only having twice as much as it currently has, would we have had a planet that was suitable for technological life? Technology requires dry land. And it's quite likely that the precise amount of water that the Earth just happens to have has allowed a technological species like we Homo sapiens to spring forth.
The world as we know it exists because a blizzard of comets and asteroids delivered just the right amount of water about 4 billion years ago. And just maybe, the same thing is happening right now somewhere else in the universe. One thing's for sure, there is plenty of water out there.
Hydrogen, the most common atom in the universe, and oxygen, one of the next most common atoms in the universe, H2O, is certainly going to be a very popular molecule, and indeed it is, within our universe.
So, water is everywhere in the universe, and we're discovering that planets are too. But we still haven't found another planet with liquid water. Scientists have discovered more than 400 new planets. None of them look like our world.
What we have not yet found is a planet that is about the same size and mass and chemical composition as the Earth orbiting another star. So it remains an extraordinary holy grail for humanity to find other abodes that remind us of home.
But we'll keep looking. We know that there are around 200 billion stars in our galaxy alone. And as many as 40 billion of them could have planets.
We're still hopeful that when we discover terrestrial-style planets, that will help us tremendously in understanding how our own inner solar system planets and the Earth evolved in comparison to the outer solar system planets.
We are entering into what is going to be thought of in the future as the golden age of planetary discovery. We will really, for the first time, begin to truly understand the actual diversity that lies out there. I think it's going to be a fantastically exciting time.
Planets form according to the laws of physics and chemistry. What they become, that has a lot more to do with luck. Many scientists believe it's only a matter of time before we find another planet like Earth. One that formed from the same ingredients in the right place with just the right amount of water. One thing's for sure, there are billions of planets out there waiting to be discovered.